Okay, remarkably, the fundamental theorem of calculus creates a bridge between differentiation and integrals, or the area underneath the curve. So these are kind of inverses of each other, which means that if I have a rate, for instance, a velocity, then I can recover my original position function by anti-differentiating, and I can find differences in that position function by viewing this as the area underneath the function. So this is why when we found antiderivatives to functions, we used the same symbol that we did to estimate areas between curves. Because the area between 2 points underneath the function can be found by finding an antiderivative and evaluating the difference between those two. So let's put this into practice. It's interesting in either way, right? You can find the area underneath the function by finding an antiderivative and evaluating the difference. But you can also start with a rate and find the original function by anti-differentiating. It's pretty cool. Here, our spaceship's velocity measured in meters per second is given by this quadratic right there. Okay, so we want to find the change in our position. So again, I'll copy that down, what I just erased. The area underneath the velocity curve, right? The area underneath the rate is the change in the original function. So if I integrate my rate, I get a change in my position function. So that's what we want to do. We want to find the change in the position function by integrating the velocity curve as time travels from 1 to 7. Right? And I can do this by finding an antiderivative and evaluating the difference. So let's do this. I want to integrate from 1 to 7. V of t is equal to 2 times t squared minus 9t. All right, we will find an antiderivative. So this will be 2/3 t cubed minus 9/2 t squared. Now, if I was to find any antiderivative or the general antiderivative, I would add that plus c. But for reasons that we've talked about in class, that plus c doesn't matter when you have a definite integral. So I want to take just any antiderivative. So why not just plus 0? I'm going to take this antiderivative and evaluate it at the 2 points. Oh, I don't know why that reads 1. Should be 7. I want to evaluate it from 1 to 7. So I'm going to take this function at 7, 2/3 7 cubed minus 9/2 times 7 squared, and I will subtract that antiderivative at the bottom of my integral at 1, 2/3 1 cubed minus 9/2 times 1 squared. All right, so when the algebra clears the room, we get a 12. So notice that whenever we went from velocity, a rate, to our position function, we went up by a power. So instead of meters per second now, it's just measured in meters. Right, that's the change in your position. You traveled 12 meters between time is equal to 1 and time is equal to 7.